An invisible force from the sun controls far more than the light in our sky. It dictates the fate of our technology, our health, and the very course of human history. From the auroras dancing over the poles to the sudden collapse of entire power grids, space weather is a fundamental driver of civilization. This journey will uncover 40 extraordinary ways these cosmic phenomena have shaped our world, revealing a hidden connection between the heavens and our daily lives. You will discover how ancient explorers were guided by solar storms and why a single event could threaten our modern world. What unseen celestial message do you think our ancestors missed? Our story begins not with modern satellites, but with ancient sailors navigating by starlight on open seas. These early explorers possessed an intimate knowledge of the heavens, yet they were guided by an invisible force they could never have named. When the sun unleashed a powerful storm, the resulting geomagnetic turmoil would paint the sky with spectacular, shifting auroras. For a Viking navigator in the North Atlantic, a sudden, brilliant glow on the horizon could be mistaken for the first light of dawn. This celestial deception, a false dawn conjured by a solar tantrum, had the power to alter destiny. A ship's crew, believing land was near, might change course toward an illusion, only to be lost in the endless ocean. Or conversely, they might interpret the shimmering curtains of light as a divine signal, a message from the gods urging them toward a new and unknown shore. We see hints of this in the sagas, where the aurora borealis was described as the armor of Valkyries, a supernatural omen that directly influenced where voyages ended and settlements began. This was the first way space weather shaped our world, by subtly twisting the paths of human migration and discovery. The sun was a silent navigator, its moods charting courses we believed were our own. This celestial storytelling did not end with the Vikings. Across the frozen expanses of the Arctic, the Inuit peoples watched the same shimmering skies and saw something profoundly different. To them, the aurora borealis were the spirits of their ancestors, joyful souls playing a game of football with a walrus skull across the heavens. The crackling sounds sometimes heard during intense displays were the voices of these spirits. This belief was not mere superstition. It was a fundamental pillar of their culture, influencing community rituals, storytelling traditions, and a deep, respectful relationship with the natural world. Their entire cosmology, their sense of place in the universe, was shaped by a phenomenon born from solar particles colliding with Earth's magnetic field. On the other side of the world, in medieval Europe, the very same lights ignited a much darker fear. Interpreting the blood red and green hues dancing in the night as divine wrath or a prophetic omen, populations saw portents of coming war, plague, or famine. These perceptions directly affected public morale and could even influence the decisions of kings and generals, who might delay a battle or call for days of prayer based on a celestial sign they could not understand. In this way, space weather forged collective identities. It gave one culture a connection to its past and another a deep-seated anxiety about its future. The stories we tell about the sky are a powerful testament to its influence on the human imagination. But what happens when these celestial forces move beyond folklore and begin to directly interfere with our most fundamental means of connecting with one another? That same celestial power that inspired myths and fears soon revealed a far more tangible threat. The year was 1859, and the world was being connected for the first time by a web of copper wires, the telegraph. This was the nervous system of a new global age, carrying news and commerce at the speed of electricity. Then, in the first days of September, the sky erupted. Auroras, normally confined to the poles, blazed so brightly over the Caribbean and Hawaii that people could read newspapers by their light at midnight. But this beautiful display was the herald of chaos. The true storm was not in the sky, but coursing through the very wires humanity relied upon. Telegraph systems across North America and Europe spectacularly failed. Operators received severe electric shocks from their equipment. Paper strips in telegraph offices spontaneously caught fire, and pylons threw sparks like miniature lightning storms. In some cases, the geomagnetic-induced currents in the lines were so powerful that operators found they could disconnect their batteries and still send messages, running their telegraphs on pure celestial power. This was the Carrington event, a solar superstorm, and it marked the third way space weather shaped our civilization by demonstrating our profound technological vulnerability. The Internet of the 19th century was brought to its knees by a blast of plasma from the sun. For the first time, engineers and scientists were forced to confront an uncomfortable truth. Our greatest inventions could be disabled by a force from 93 million miles away. The lessons scribbled in the logbooks of those stunned telegraph operators were a stark warning, one that would echo into a future they could never have imagined, a future built on an even more delicate and pervasive web of electrical circuits. The silent threat that crippled telegraph wires in the 19th century has only grown more potent. Today, our civilization is powered by a vast, interconnected web of high-voltage power grids, a network infinitely more complex and vulnerable than the simple copper lines of the past. A severe geomagnetic storm does not just send sparks flying from a single wire. It can generate massive, slow-moving electrical currents in the ground itself. These currents, called geomagnetically induced currents, seek the path of least resistance, flooding into the extensive metal arteries of our power grids. The most dangerous component of our electrical system, the massive transformers that step voltage up for transmission and down for distribution, are not designed to handle this kind of direct current intrusion. They can overheat, their internal wiring melting in a matter of minutes, leading to catastrophic and permanent failure. Replacing these multi-ton giants is not a simple task. Each one is a custom-built piece of engineering that can take months or even years to manufacture and install. The fourth way space weather shapes our world is by holding a sword of Damocles over the entire foundation of modern life, our electrical power. We have already had a chilling preview of this vulnerability. In March of 1989, a powerful solar storm slammed into Earth's magnetic field. The resulting geomagnetic currents surged into the Hydro-Quebec power grid in Canada. Within seconds, protective systems were overwhelmed. The entire grid collapsed, plunging 6 million people into a sudden, deep blackout that lasted for 9 hours in the depths of a Canadian winter. The event was a wake-up call, a direct demonstration that a burst of energy from the sun could, in an instant, erase the technological comforts of an entire region. In response, utility companies worldwide have begun investing heavily in forecasting and mitigation. They employ sophisticated models to predict space weather and can, if given enough warning, implement protective measures. These include temporarily reducing the load on the grid or activating special hardware designed to block these destructive Earth currents. This entire defensive strategy hinges on one critical capability: knowing when the storm is coming. Our ability to keep the lights on now depends on a chain of observatories and satellites watching the sun, a topic that reveals our next crucial line of defense. This constant battle against the sun's influence extends far beyond our power grids, reaching high into the vacuum of space itself. The very region we consider empty is a dynamic environment, its density controlled by the sun's temper. When our star erupts with solar flares and coronal mass ejections, it sends a flood of extreme ultraviolet and X-ray radiation toward Earth. This energy slams into our upper atmosphere, causing it to heat up dramatically and, like a hot air balloon, expand outward. For the thousands of satellites whizzing around our planet in low Earth orbit, this expansion is a serious problem. The tenuous gases at the edge of our world suddenly become thicker, creating a noticeable headwind. This increased atmospheric drag acts as a constant, invisible brake, slowly but surely sapping a satellite's speed and pulling it downward. To avoid a premature and fiery death in the lower atmosphere, mission controllers must frequently fire small onboard thrusters, a process known as a reburn, to boost the satellite back into its proper orbit. Each of these maneuvers burns precious fuel, directly shortening the satellite's operational life and adding hundreds of millions of dollars in costs over time. Even the massive International Space Station, orbiting at an altitude of around 250 miles, is not immune. It requires regular reboosts to counteract this solar-induced decay, a stark reminder that the sun's reach touches every aspect of our presence in space. This is the fifth way space weather shapes our world, by dictating the lifespan and economics of the orbital infrastructure that modern society depends on for weather forecasting, global communications, and Earth observation. And this celestial tug of war over a satellite's position has a direct and surprising consequence for anyone who has ever used a smartphone to navigate an unfamiliar city, because the precision of your GPS signal is hanging in the balance. That same atmospheric drag that tugs at satellites creates a turbulent sea of charged particles right here in our own sky. This region, the ionosphere, is where the sun's radiation strips electrons from air molecules, creating a swirling, electrically active layer of plasma. And it is precisely through this chaotic sea that the delicate signals from GPS satellites must travel to reach your phone or the navigation system in your car. When the sun is calm, the journey is relatively stable, but when a solar storm hits, the ionosphere erupts into a tempest of density changes and swirling currents. This sixth-way space weather shapes our world is by degrading the very precision of our global positioning system. The signals, which travel at the speed of light, get bent and delayed as they pass through these disturbed layers. A signal that should take a precise amount of time to reach you suddenly arrives a fraction of a second late. To your GPS receiver, that tiny delay translates into a positioning error, not of inches but of several meters, or in a severe storm, even tens of meters. A pilot relying on GPS for a low visibility approach could find themselves dangerously off course. A shipping container vessel navigating a narrow channel could be guided toward a sandbar. The disruption even strikes at the heart of global finance, because GPS satellites also provide the hyper-accurate timing signals that synchronize transactions across stock markets. A microsecond of drift could throw this delicate clockwork into disarray. To fight back, scientists have developed complex models of the ionosphere, constantly updated with data from ground stations and satellites, trying to predict and correct for the sun's interference in real time. Our ability to know exactly where we are, a modern miracle we often take for granted, is locked in a constant, invisible battle with the weather in space. And this battle for location is just one front in a much larger war, one being waged for the health of the astronauts living and working directly in the line of fire. The sky above is not as empty as it appears from the comfort of your airplane window. At the cruising altitudes of long-haul flights, the thin air provides far less protection from the constant rain of radiation from space. This becomes a critical issue on the polar routes, the great circle paths that connect continents like North America and Asia by flying over the Arctic. While these routes save countless hours and millions of tons of fuel, they place aircraft directly in the line of fire during solar storms. The Earth's magnetic field, which funnels and traps charged particles toward the poles, creates a natural funnel for this radiation. During a solar particle event, when the sun hurls billions of tons of high-energy protons toward us, the radiation levels at high altitudes can spike dramatically. These subatomic bullets can easily penetrate the aluminum skin of an airliner, exposing passengers and crew to a significantly higher dose of ionizing radiation. For the occasional traveler, this poses a minimal risk comparable to a medical X-ray. But for flight crews who work these routes for years, the accumulated exposure becomes a serious occupational health concern, with studies linking it to a higher incidence of certain cancers. This is the seventh way space weather shapes our world, by posing a silent, invisible risk to human health 30,000 feet above the ground. The response to this threat is both practical and costly. Space weather forecasters at centers like NOAA Space Weather Prediction Center now provide specific alerts for the aviation industry. When a major solar radiation storm is underway, airlines receive warnings and must make a critical decision. They can choose to reroute their polar flights to lower latitudes, where the Earth's magnetic shield provides better protection. This action safeguards the people on board, but it comes at a steep price, burning extra fuel and adding hours to the journey, a cascade of delays and expenses that ripple across the global travel network. The same particles that paint the serene auroras over the Arctic directly dictate the flight paths and schedules of modern aviation, a powerful reminder that the sun's influence touches even our most routine journeys. And as we look for ways to protect ourselves from this celestial barrage, we find ourselves turning to a much older form of communication, one that once connected empires and now holds the key to resilience in the digital age. The same cosmic particles that threaten our technology and health also write their signature deep into the planet's climate. While the sun's steady output is the engine of our weather, its long-term moods, the rhythmic 11-year cycle of sunspots and solar storms, can nudge global atmospheric patterns in subtle but profound ways. During periods of exceptionally low solar activity, like the Maunder minimum that stretched from the mid-1600s to the early 1700s, the sun entered a kind of prolonged quiet spell. This era, which saw very few sunspots, coincided with a climatic anomaly known as the Little Ice Age. Rivers like the Thames in London routinely froze solid, allowing for frost fairs to be held on the ice. Alpine glaciers advanced, swallowing entire villages in their path. This was not a global ice age, but a pronounced regional cooling, particularly in the northern hemisphere. The eighth way space weather shapes our world is through its indirect but powerful influence on climate, and by extension, the very foundation of human society, our food supply. Those colder temperatures shortened growing seasons and led to repeated crop failures. Failed harvests of wheat and rye across Europe triggered widespread famine, economic turmoil, and mass migration. History records the years without a summer, the great famines that toppled governments and sparked social unrest, and in the background of it all was a strangely quiet sun. The mechanism is still being unraveled by scientists. It appears that reduced solar ultraviolet radiation alters the temperature and wind patterns in the upper atmosphere, which then cascade downward to affect weather systems we feel on the surface. There is also a fascinating hypothesis linking cosmic rays to cloud formation. When the sun is active, its strengthened magnetic field helps shield Earth from these high-energy rays from deep space. Fewer cosmic rays might mean fewer of the tiny particles that seed cloud droplets, potentially leading to less cloud cover. But during a solar minimum, with that shield weakened, more cosmic rays penetrate our atmosphere, possibly encouraging more low-level clouds that can cool the planet. Whether through this complex chain of events or other atmospheric shifts, the Sun's long-term variability has repeatedly acted as a hidden hand on the global thermostat, shaping agricultural prosperity and despair. This historical link between a quiet sun and a hungry world forces us to look beyond the immediate technological threats and consider a more fundamental biological vulnerability. What happens when these same cosmic forces bypass the atmosphere and directly target the intricate chemistry of life itself? This constant, unseen rain from the cosmos does not stop at the edge of space or the roof of an airliner. It reaches all the way down to the ground where we live, a faint but persistent background hum of radiation that is part of the very fabric of our environment. The intensity of this cosmic drizzle is not constant. It ebbs and flows with the Sun's 11-year cycle of activity. When the Sun is at its minimum, its magnetic field weakens, pulling back a protective shield that normally deflects some of the most energetic particles hurled at us from distant supernova. These are galactic cosmic rays, and with the Sun's guard down, more of them punch through to the upper atmosphere, spawning a shower of secondary particles that sprinkle down to the surface. This is the ninth way space weather shapes our world, by subtly modulating the natural radiation dose every single person on the planet receives. The increase is minuscule, far less than what you would get from a medical X-ray or even from the radon gas that can accumulate in some basements. Yet, because it is a global phenomenon affecting billions, even a tiny statistical shift is studied with intense interest. Some epidemiological research has explored possible, highly subtle correlations between periods of high cosmic ray flux and small increases in certain health issues, though the evidence remains controversial and the effect is dwarfed by everyday risks like diet or air pollution. The true danger of this particle rain is revealed not on Earth, but when we leave its protective atmosphere behind. For astronauts on the International Space Station, and especially for future travelers to the Moon or Mars, this radiation is not a background whisper but a roaring torrent. Outside the safe cocoon of Earth's magnetic field and thick atmosphere, they are exposed directly to the full fury of the Sun's storms and the relentless barrage of galactic cosmic rays. These high-energy particles can tear through a spacecraft hull and the human body alike, damaging cells and DNA in ways that significantly increase the long-term risk of cancer, cataracts, and central nervous system problems. Managing this existential threat is the primary engineering challenge for deep space exploration. Every mission plan, every gram of a spacecraft's mass, is scrutinized for its radiation shielding properties. Engineers test layers of water, polyethylene, and even innovative materials to block these invisible bullets. A mission to Mars would require a spacecraft with a storm shelter, a small, heavily shielded compartment where astronauts would hunker down during a solar particle event, waiting out the celestial storm. The dream of living on other worlds is fundamentally a question of how we can design habitats that protect human biology from the same cosmic forces that have, for millennia, invisibly shaped our lives here at home. This relentless cosmic bombardment has forced human ingenuity to its absolute limits, sparking a revolution in how we build and protect our technology. The 10th extraordinary way space weather shapes civilization is by directly accelerating our technological innovation, particularly in the field of advanced shielding. Confronted by the invisible bullets of solar radiation and cosmic rays, scientists and engineers could not rely on simple slabs of metal, which can actually make the problem worse by creating a dangerous spray of secondary particles when struck. The answer was found at the molecular level, they developed new classes of hydrogen-rich polymers, plastics whose chemical structure is packed with tiny hydrogen atoms. These atoms act like microscopic shields, absorbing the energy of incoming radiation and dispersing it harmlessly without creating further fragmentation. The innovation did not stop there. Researchers are now experimenting with regenerative materials, substances inspired by human skin that can actually heal themselves after being damaged by radiation, sealing microscopic cracks and holes to maintain their protective integrity over long-duration missions. The remarkable thing is that these breakthroughs, born from the need to survive in space, are already cascading back to Earth with profound benefits. In medicine, the same principles used to shield a satellite's computer brain are being adapted to create more precise and safer radiation therapy for cancer patients, protecting healthy tissue while targeting tumors. The drive to protect data centers from the electromagnetic pulses of a severe geomagnetic storm has led to the creation of ultra-resilient server farms, fortifying the global cloud that holds everything from our financial records to our family photos. The very threat that seeks to destroy our electronic civilization is paradoxically forcing us to build a tougher, more resilient one. This constant push for protection, however, comes with an immense price tag, a financial reality that reveals the next hidden cost of our stormy relationship with the sun. The staggering cost of protecting our technology from the sun pales in comparison to the price of failing to do so. Every protective measure, every hardened satellite component, and every grid mitigation strategy represents a multi-billion-dollar insurance policy taken out against our star. This is the 11th extraordinary way space weather shapes civilization through its profound and pervasive economic impact. A single major solar storm, one on the scale of the 1859 Carrington event, could inflict not billions but trillions of dollars in damage across the globe. The cascade of failure would be instantaneous and overwhelming. The collapse of continental power grids would halt manufacturing, paralyze transportation, and freeze financial markets. The loss of satellites would cripple global logistics, banking, and communications, creating an economic blackout that could take years to recover from. We have already seen a smaller-scale version of this. The 1989 geomagnetic storm that blacked out Quebec cost an estimated $2 billion in immediate repairs and lost productivity, a sum that would be far greater today. Because of this clear and present danger, entire industries now factor space weather into their financial calculus. Insurance companies model the risk to set premiums for utilities and satellite operators. Agricultural giants, whose precision farming relies on GPS and satellite weather data, assess the potential for crop losses from a prolonged navigation or communication outage. Governments worldwide allocate hundreds of millions annually to fund monitoring networks and early warning systems, recognizing that this spending is a fraction of the catastrophic cost of being unprepared. The economic footprint of space weather is a silent but powerful variable in global financial stability, a hidden tax imposed by the cosmos on our technological ambition. This modern understanding of cost forces us to look backward to a time when the greatest economic loss was not in dollars but in knowledge. The same cosmic particles that threaten our satellites leave a permanent record deep within the Earth itself. Locked away in the ancient ice of Greenland and Antarctica and etched into the growth rings of thousand-year-old trees lies a detailed history of the sun's past fury. Scientists drill deep into ice sheets, extracting cores that contain layers of snowfall from millennia ago. Within that ice, they find a specific isotope, beryllium-10, a form of the element beryllium that is created when powerful cosmic rays smash into atoms in our atmosphere. When the sun is quiet and its magnetic shield is down, more cosmic rays reach Earth, and the concentration of beryllium-10 in the ice increases. In the same way, living trees absorb carbon dioxide from the air, trapping within their annual growth rings another isotope, carbon-14, which is also produced by cosmic rays. By analyzing the precise levels of these isotopes in tree rings and ice layers, researchers can pinpoint the exact years when the Sun was in a deep slumber or when it unleashed a superstorm. This is the 12th way space weather shapes our civilization by leaving a celestial paper trail that allows us to reconstruct its history. These natural archives have revealed colossal solar storms, events far more powerful than the Carrington event that struck our planet long before the invention of the telegraph. One such event, discovered in ice core data, is believed to have hit around 774 AD, an event so intense it would have dwarfed anything we have recorded in modern times. This paleoclimatology of space weather provides a crucial and humbling perspective. It tells us that the violent events we fear are not anomalies, but part of the Sun's normal, long-term rhythm. Our few centuries of technological civilization have simply been lucky, existing during a relatively calm period in a much stormier cosmic cycle. This knowledge is our greatest asset, transforming space weather from a mysterious threat into a predictable force of nature. Just as we study hurricane patterns to prepare coastal cities, we now study these ancient records to understand the true worst-case scenario, allowing us to build a future that is not just reactive but truly resilient. That profound connection between the cosmos and human emotion has always found its purest expression not in science, but in art. For centuries, the breathtaking spectacle of the aurora has served as a universal muse, igniting the imaginations of poets and painters alike. In the ancient Norse sagas, the northern lights were not just pretty colors, they were the Bifrost Bridge, a flaming pathway for the gods, or the gleaming armor of the Valkyries as they carried fallen heroes to Valhalla. This was not mere description, it was a profound attempt to give cosmic meaning to a phenomenon that defied simple explanation. Centuries later, during the Romantic era, this celestial inspiration reached a fever pitch. Artists like the Norwegian painter Peder Borch, facing the stark beauty of the Arctic, stood for hours in the freezing cold, trying to capture the ethereal, almost spiritual quality of the light dancing across the ice. His paintings are not literal records, they are emotional transcripts filled with a sense of the sublime, that strange mix of awe, terror, and wonder that humans feel when confronted with a power infinitely greater than themselves. The 13th way space weather shapes our civilization is by fueling our creative spirit, embedding the beauty and terror of the cosmos directly into our cultural heritage. From the vivid metaphors in Inuit storytelling to the dramatic, swirling skies in the canvases of Romantic painters, these celestial displays have been a constant wellspring for art and literature. They channel our deepest questions about divinity, mortality, and our place in the universe into tangible forms we can share. This artistic legacy is a powerful testament to a simple truth. The sun's influence is not just physical, it is deeply psychological. It touches something primal within us, a chord of wonder that resonates across generations and cultures. But what is the deeper psychological mechanism behind this profound sense of awe, and how does it subtly steer the course of our daily lives and collective decisions? The same awe that inspired ancient artists is a tangible force that can rewire our modern minds. Standing under a grand auroral display, watching those silent, shimmering curtains of light ripple across the heavens does something more than just please the eye. It can trigger a profound psychological state known as awe, a feeling of being in the presence of something vast that completely transcends our ordinary understanding of the world. Researchers studying this emotion have found it has remarkable effects on human psychology, Experiencing genuine awe, whether from nature, art, or the cosmos, has been shown to promote a greater sense of well-being, significantly reduce stress levels, and perhaps most importantly, increase prosocial behaviors, making people more generous, cooperative, and connected to their community. In that moment of cosmic wonder, your personal worries and trivial daily concerns seem to shrink in scale against the immense backdrop of the universe. This is the 14th extraordinary way space weather shapes our civilization, by indirectly nurturing human happiness and social cohesion through the sheer, breathtaking beauty of its manifestations. That flash of green and purple in a dark sky is not just a physical phenomenon, it is a therapeutic event. It forges a connection between the cosmos and the human mind that is just as real and just as vital as the connection between a solar flare and a failing power grid. One threatens our infrastructure, while the other quietly fortifies our inner resilience, reminding us that we are part of a story much larger than ourselves. This global need for foresight has birthed an entirely new industry, one that operates in the silent language of solar data and geomagnetic forecasts. The 15th extraordinary way space weather shapes our civilization is by creating a specialized global enterprise dedicated to prediction. This is not a single organization, but a vast, interconnected ecosystem of government space agencies, private companies, and university research labs, all working in concert to watch the sun. At the heart of this effort in the United States is the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, an operations hub that functions much like a national weather service for the cosmos. Their forecasters analyze a constant stream of data from a fleet of sun-watching satellites, like the Deep Space Climate Observatory, stationed 1 million miles upstream from Earth. When these monitors detect a massive coronal mass ejection bursting from the sun's surface, the center swings into action, calculating its speed, trajectory, and potential impact time. These are not abstract bulletins for scientists. They are actionable warnings sent directly to the industries on the front lines. A satellite operator receiving an alert of an incoming radiation storm can command their billion-dollar asset to enter a protective safe mode, turning its delicate electronics away from the particle blast. A power grid manager, warned of approaching geomagnetic turbulence, can proactively reduce the electrical load on the grid or activate systems to block destructive currents. This entire forecasting industry, employing thousands of scientists, engineers, and data analysts worldwide, is a direct economic response to our planetary vulnerability. We have turned a cosmic threat into a field of human employment and technological innovation. This predictive shield is now absolutely essential because the next system it must protect is the very circulatory system of our global society, the delicate web of communications that binds us all together. That same turbulent ionosphere that scrambles our GPS signals holds another critical role, acting as a celestial mirror for long-distance radio waves. High-frequency radio signals used by pilots over the oceans, ships in remote seas, and amateur radio operators connecting continents do not travel in straight lines. Instead, they are bounced between the ground and this electrically charged layer of the upper atmosphere, skipping their way around the curve of the Earth. This natural relay system allows communication across thousands of miles without any physical infrastructure. But when the sun erupts with a powerful flare, it unleashes a blast of X-rays that slams into the ionosphere. This sudden influx of energy supercharges the lower region, the D layer, causing it to absorb high-frequency radio waves like a thick sponge instead of reflecting them. The signal that was once gracefully bounced from continent to continent is now swallowed whole, vanishing into the static. This is the 16th extraordinary way space weather shapes our civilization, through the sudden and complete disruption of high-frequency radio communications. A commercial airliner flying a transoceanic route can find its primary communication link severed without warning. A maritime emergency distress call might never reach the shore. These blackouts can last from a few minutes to several hours, creating pockets of radio silence across the globe precisely when clear communication is most vital. Our response to this vulnerability has been to build a new network in the sky, a constellation of communication satellites that bypass the ionosphere entirely. Yet this solution creates its own profound dependency, as we have seen, on technology that is itself exquisitely sensitive to the sun's other tantrums. This reliance on a natural system that both enables and threatens us is a recurring theme, one that extends even to the massive metal arteries buried deep within the Earth. Buried deep beneath our feet, a silent and relentless decay is underway. The same geomagnetic currents that threaten our power grids find another perfect conductor in the thousands of miles of metal pipelines crisscrossing the continents. These arteries of our energy supply, carrying oil and natural gas, inadvertently act as giant antennas during a solar storm. The slow-moving electrical currents induced in the ground by these celestial events seek the path of least resistance, flooding into the pipeline steel walls. This is not a sudden, dramatic failure like a blackout, but a slow, insidious form of erosion. The unwanted electrical flow accelerates a process called electrolytic corrosion, literally causing the metal to be eaten away molecule by molecule from the inside out. A pipeline that should last for decades can see its lifespan cut short, developing weak points and pinhole leaks that threaten both the environment and public safety. A single rupture in a remote area can spill thousands of barrels of crude oil into pristine wilderness, a disaster with ecological consequences that last for generations. This is the 17th extraordinary way space weather shapes our civilization, by directly attacking the hidden veins of our energy infrastructure. To fight back, pipeline operators wage a constant, invisible war. They use a technology called cathodic protection, a system that imposes a small electrical voltage on the pipe to counteract the corrosive currents trying to flow off it. It is a delicate balancing act, and during a severe geomagnetic storm, that balance is completely shattered. The solar-induced currents can overwhelm the protective systems, leaving the pipeline utterly vulnerable. This forces companies to invest hundreds of millions in monitoring networks, sophisticated sensors that track both pipeline health and real-time geomagnetic activity, allowing them to adjust their defenses when a storm is coming. The economic impact is immense, a perpetual and hidden cost of maintenance and monitoring passed down through the entire energy supply chain, linking the solar wind directly to the price we pay for fuel and the security of our energy supply. This slow, corrosive threat stands in stark contrast to the next arena of solar impact, where the damage is measured not in years, but in milliseconds, and the stakes are not buried in the ground, but flashing on computer screens across the globe. The relentless search for precision in our global markets has created a new and invisible vulnerability. Every stock trade, currency exchange, and financial transaction is now stamped with a hyper-accurate timestamp, a digital fingerprint that establishes its exact order in a torrent of electronic commerce. These crucial timing signals, synchronized to within a millionth of a second, are not generated on Wall Street or in the City of London. They are beamed down from the constellation of Global Positioning System satellites orbiting high above the Earth. This celestial clock is the silent, beating heart of modern capitalism. But as we have seen, the path from space to your broker's computer is a turbulent journey through the ionosphere. When a solar storm distorts this layer, it does not just shift a location pin on a map, it delays the arrival of that all-important timing signal. A microsecond of drift might seem trivial, but in the world of high-frequency trading, where algorithms execute millions of orders in the blink of an eye, it is an eternity. Two identical trades can now arrive in the wrong order, triggering massive losses, creating settlement failures, and potentially cascading into a systemic risk that threatens the stability of entire markets. This is the 18th extraordinary way space weather shapes our civilization by threatening the temporal foundation of our global financial system. The response from the financial sector has been a quiet, multi-billion-dollar arms race for precision. Major trading hubs and data centers now install their own backup atomic clocks, creating a terrestrial network of ultra-precise timekeepers to guard against a celestial delay. They are literally building a parallel timekeeping universe on the ground, all to insulate the flow of capital from the moods of our star. This profound dependency on cosmic timing echoes far beyond the trading floor, reaching into laboratories and observatories where scientists push the very boundaries of human knowledge, seeking answers to questions that also depend on a perfectly synchronized universe. That same celestial static that disrupts our financial clocks also obscures our view of the cosmos. The 19th extraordinary way space weather shapes our civilization is by directly impeding our quest for fundamental knowledge, placing a veil between our telescopes and the distant universe. For astronomers using ground-based observatories, a clear, dark night is only half the battle. When the sun is active, it floods the sky with an invisible noise across various wavelengths, creating a background hiss that can drown out the faint whispers of light from galaxies billions of light years away. The situation is even more challenging for radio astronomers, whose massive dishes listen to the radio songs of stars and nebulae. The same turbulent ionosphere that disrupts GPS and radio communications acts like a funhouse mirror for these cosmic signals, bending and distorting them before they can be recorded. To obtain clean data, astronomers must become celestial schedulers, planning their precious observation time around the sun's forecast, waiting for those precious windows of solar calm. The challenge does not end on the ground. The most powerful observatories, like the Hubble Space Telescope, orbit above our atmosphere, but they are still exposed to the full brunt of solar radiation. Energetic particles from a solar storm can slam into their sensitive detectors, creating bright speckles and streaks across the image, as if someone had thrown digital gravel at the lens. Over time, this relentless bombardment degrades the very instruments we rely on to see the farthest reaches of space. Our entire understanding of the universe, from the life cycles of stars to the nature of dark energy, is therefore filtered through the variable and often noisy state of our own star. Every profound discovery is made possible not just by human ingenuity, but by our ability to peer through the sun's interference, using sophisticated correction algorithms and heavy shielding to subtract its influence from the data. This constant struggle for a clear view mirrors the challenges now faced by a new generation of celestial travelers, as the nascent space tourism industry must also learn to navigate the sun's unpredictable storms. The same cosmic radiation that threatens astronauts now looms over the first tourists booking tickets to the edge of space. For companies launching civilians into the heavens, space weather is not an abstract scientific concern. It is the most critical factor in their safety protocol and their very business model. A sudden solar particle event during a flight could expose passengers to radiation doses far exceeding safe limits, turning a joyride into a medical emergency. This 20th extraordinary way space weather shapes our civilization is by dictating the safety and economic viability of the nascent space tourism industry. In response, every vehicle, from a Blue Origin New Shepard capsule on its suborbital arc to a SpaceX Dragon orbiting for days, is designed with this invisible threat in mind. Their hulls incorporate advanced shielding materials, the very polymers developed for satellites, to block the most dangerous particles, but engineering alone is not enough. The entire launch schedule for commercial spaceflight is now synchronized with the sun's forecast. Mission control rooms for these companies display real-time data from solar observatories right alongside their own vehicle telemetry. A warning of an impending solar storm will force a launch to be scrubbed, sometimes with only hours to spare, grounding flights just as a terrestrial hurricane closes an airport. This operational reality has a direct and profound impact on the bottom line. The cost of insuring a single flight or the entire company is calculated based on space weather risk models. A period of predicted high solar activity can send insurance premiums skyrocketing, making each ticket more expensive and threatening the industry's long-term growth. The dream of opening the cosmos to everyone is therefore tethered to our ability to understand and predict the ancient, stormy heart of our star. And this celestial influence reaches back down to Earth, into our pockets and homes, affecting the very devices we use to watch these historic launches. The very devices you rely on are not safe from the sun's distant tantrums. A single high-energy particle, a cosmic ray from a distant supernova or a proton flung from a solar storm, can pierce the atmosphere and strike the heart of a modern microchip. When this subatomic bullet hits a sensitive memory cell, it can deposit enough electrical charge to flip a single binary digit from a 0 to a 1, or a 1 to a 0. This phenomenon is known as a single event upset, a silent, invisible bit flip that corrupts data without any physical damage to the device. For most of us, this might manifest as a mysterious, one-time computer glitch, a crashed application, or a corrupted photo file, an unexplained digital hiccup we usually blame on a software bug. But the implications run far deeper. In critical control systems, such as those managing a factory's automated assembly line or the flight controls of a modern airliner, a single corrupted bit in the wrong place could, in theory, issue a catastrophic command. This is the 21st extraordinary way space weather shapes our civilization, by directly threatening the integrity of the data that powers our digital world. As manufacturers relentlessly shrink transistors to make our electronics faster and more powerful, they also make them exponentially more vulnerable to these cosmic strikes. A smaller transistor requires less electrical charge to operate, which also means it takes a much smaller particle hit to flip its state. This relentless push for miniaturization is an unintended invitation for celestial interference. In response, the industry is being forced to innovate, designing radiation-hardened components with special error-correcting codes and redundant circuitry for use in everything from medical implants to spacecraft. This invisible war, fought at the nanoscale, is a constant reminder that the pristine logic of our digital universe is built on a foundation that is perpetually bombarded by the chaos of the cosmos. The integrity of the data on your hard drive is as fragile as the stability of the massive transformers that hum at the heart of our power grid. The fragility of our digital world pales before the brute force threat to its physical heart. A severe solar storm does not just corrupt bits of data, it can physically melt the multi-story transformers that form the backbone of our continental power grids. These are not simple components you can replace from a warehouse shelf. Each high-voltage transformer is a custom-engineered behemoth, weighing hundreds of tons, built to order with lead times that can stretch to 18 months or more. Their intricate windings of copper and electrical steel are precisely calibrated to handle the alternating current of our daily use. but they are defenseless against the slow, direct current pushed into the ground by a geomagnetic storm. That foreign current causes the transformer's core to saturate, overheating it from the inside out. The insulation begins to smoke, the copper windings can melt into a solid block, and in a worst-case scenario, the unit can explode, spewing toxic coolant and rendering itself a permanent loss. The 22nd extraordinary way space weather shapes our civilization is by creating the potential for a cascade of transformer failures that could lead to a blackout of unimaginable scale and duration. Imagine not a blackout that lasts for a night, but one that persists for months across entire nations. Without power, the pumps that deliver water and fuel cease to function. Refrigeration and supply chains break down. Healthcare systems revert to a pre-industrial age. This is the single greatest catastrophic risk posed by our star. In response, organizations like the North American Electric Reliability Corporation have developed mandatory standards for grid operators, requiring them to assess their vulnerability and install protective devices. Yet the sheer scale of the grid and the astronomical cost of hardening every critical node means the risk remains a top-tier concern for national security agencies worldwide. Our technological civilization has, in its dependence on these colossal machines, created a single point of failure forged in the heart of the sun. Mitigating this existential threat cannot be a national endeavor alone, for a storm does not recognize borders, forcing a conversation about one of our most vital and fragile human creations, the interconnectedness of our global community itself. This invisible threat has forged an unprecedented alliance among nations. The 23rd way space weather shapes our civilization is by compelling international cooperation on a global scale. No single country can shield itself alone from a coronal mass ejection, a force that sweeps past borders and continents with impartial power. This shared vulnerability has broken down decades of political barriers, creating a silent, continuous dialogue in the language of solar data. Space agencies that might otherwise be rivals, including NASA, the European Space Agency, and Roscosmos, now operate a shared fleet of solar sentinels. Satellites like the Solar and Heliospheric Observatory and the Deep Space Climate Observatory provide a constant, unbroken watch on the sun, their data streams pooled into a common resource for all humanity. This cooperation is formalized through treaties and agreements managed by bodies like the United Nations Committee on the Peaceful Uses of Outer Space, which has explicitly recognized space weather as a critical global challenge. A solar storm does not recognize nationality or political affiliation, and so the response must be equally universal. This collaborative spirit, born from a shared cosmic fragility, stands as a powerful positive example. It demonstrates how a celestial phenomenon can unite humanity in a common cause, fostering a quiet but resilient network of trust and shared purpose that operates every minute of every day. This intricate global web of monitoring and diplomacy, in turn, provides the essential raw material for the next critical layer of our planetary defense, the effort to translate complex solar data into a clear and urgent message for the public. This push for a prepared public has transformed planetariums from simple star theaters into frontline classrooms for cosmic readiness. The 24th extraordinary way space weather shapes our civilization is through a global mobilization of public awareness and education. Governments and scientific bodies, recognizing that a terrified population is as dangerous as a powerless one, have launched campaigns to demystify the sun's threats. They frame space weather not as a doomsday scenario, but as a manageable risk, akin to preparing for a major hurricane or earthquake. The goal is to replace fear with practical knowledge. In museums and science centers worldwide, You can now find interactive exhibits where visitors can trigger a simulated coronal mass ejection and watch its effects ripple across a global map, disrupting power grids and satellite communications. Online platforms offer webinars and downloadable toolkits, advising families on how to build an emergency kit that includes not just water and canned food, but also a battery-powered radio and backup power for communication devices. This educational drive understands a fundamental truth: an informed citizenry is the ultimate shock absorber for a society under stress. When people understand the cause of a prolonged blackout, they are less likely to panic and more likely to cooperate with community response efforts, sharing resources and supporting their neighbors. The most profound investment, however, is in the next generation. School curricula are now incorporating lessons on heliophysics and planetary defense, turning children into nascent space weather forecasters. These students learn to interpret data from classroom solar telescopes, understanding that the sunspots they sketch today could be the source of the storms they must manage as adults. This vast, ongoing project of public enlightenment ensures the hard-won knowledge of our vulnerability is not lost, but is instead passed down, building a future civilization that is not just technologically resilient, but cosmically literate. This academic focus is now reshaping the very textbooks used in classrooms. The 25th extraordinary way space weather shapes our civilization is by fundamentally altering academic curricula and fueling a new wave of STEM education. What began as a niche topic in astrophysics has blossomed into a full-fledged discipline, with universities worldwide offering dedicated courses in heliophysics and space weather prediction. Students are no longer just learning abstract theories about plasma and magnetic fields. They are running sophisticated computer models that forecast solar storms, analyzing real-time data from NASA satellites, and interning at power companies to help harden the grid. These research opportunities are a powerful engine for innovation, turning lecture hall concepts into hands-on solutions for a global problem. This direct line from the classroom to critical infrastructure creates a powerful cycle. It ensures a continuous pipeline of brilliant young minds entering the field, ready to protect our technological society. But this new knowledge does more than just secure our future. It gives us a new lens through which to view our past. Historians and scientists are now collaborating, re-examining ancient records of strange sky phenomena and correlating them with ice core and tree ring data. A medieval chronicle describing a blood-red aurora seen in Rome, once dismissed as superstition, can now be verified as evidence of a massive solar storm. This interdisciplinary dialogue is rewriting chapters of human history, revealing that the sun has been an active character in our story all along, its silent storms influencing events we once believed were entirely of our own making. The quest to understand our star is proving to be a journey that connects the cutting-edge lab with the dusty archive, forever changing how we see our place in the cosmos. History is being rewritten not in dusty archives, but in ice core laboratories and tree ring studies. The strange celestial events meticulously recorded by ancient scribes, once dismissed as mythology or divine portents, are now being decoded as real physical phenomena. A Chinese text from around 977 BCE describes a five-tailed star, scarlet and white, that appeared in the sky. For centuries, this was an astronomical mystery. Today, scientists cross-referencing that record with ice core data from Greenland found a massive spike in the beryllium-10 isotope from that exact period. The mysterious star was almost certainly a colossal auroral display, the visible echo of a solar superstorm that dwarfed the Carrington event. This is the 26th extraordinary way space weather shapes our civilization by giving us a new key to unlock our own past. We can now look at the accounts of Roman historians who described nighttime so bright that soldiers believed dawn had come hours early, and understand they were witnessing a severe geomagnetic storm. The red crucifix seen in the English sky before the Norman conquest, interpreted as an omen for King Harold's defeat, was likely the shimmering red glow of an intense aurora. This reinterpretation transforms our understanding of human agency. It suggests that the decisions of kings, the outcomes of battles, and the very myths that founded cultures were not solely products of human will or divine intervention, but were sometimes nudged by invisible forces from the sun. This fusion of science and the humanities creates a richer, more complete story of humanity, one where our ancestors were not just storytellers, but inadvertent witnesses to cosmic violence. By learning to read their accounts with our modern knowledge, we gain a crucial long-term record of solar behavior, a deep time perspective that is essential for the next critical step, moving from historical analysis to predicting the sun's next move with enough precision to truly safeguard our future. Those ancient chronicles of celestial fire are now the training data for our digital sentinels. To anticipate the sun's next move, scientists have built virtual stars inside some of the world's most powerful supercomputers. These are not simple animations, they are immensely complex predictive models that simulate the entire life cycle of a solar storm. They begin with the intricate physics of magnetic fields twisting on the sun's surface, calculating the exact moment a snarl of plasma might erupt as a coronal mass ejection. The simulation then tracks this billion-ton cloud as it races across the 93-million-mile gulf of interplanetary space, forecasting its speed, density, and most critically, its magnetic orientation. The final act of this digital drama plays out in the intricate dance with Earth's own magnetic shield, the magnetosphere, modeling how the shockwave will compress it and where the most dangerous electrical currents will be induced in our planet's crust. The 27th extraordinary way space weather shapes our civilization is through the monumental achievement of these predictive simulations. Their sole purpose is to buy us time, transforming a cosmic surprise into a managed event. A forecast giving days of warning allows a satellite operator to safely reposition a vital communications satellite. A prediction with just 45 minutes of lead time can be the difference between a stable power grid and a continent-wide blackout, giving engineers a precious window to activate protective systems. But these models are not static, they are living digital entities constantly learning. Every new solar storm that hits Earth provides a torrent of real-time data from a fleet of space-based observatories, data that is fed back into the system to refine its algorithms, making the next forecast even more precise. This relentless cycle of prediction and verification is a direct application of human intellect to counter a natural threat, a digital shield forged from pure mathematics and computational brute force. And as these models grow more sophisticated, they are beginning to reveal a pattern not just in our sun's behavior, but in the very star stuff that binds us to the cosmos. These silent sentinels in space form our first and only line of defense against a surprise attack from the sun. Orbiting at a point where the gravitational pulls of the Earth and Sun perfectly balance, the Solar and Heliospheric Observatory maintains a constant, unwavering gaze on our star. It is joined by a fleet of specialized observers like NAS, a solar dynamics observatory, which captures breathtaking high-definition images of the sun across multiple wavelengths every few seconds. These are not merely cameras, they are sophisticated laboratories that can peer into the sun's ferocious atmosphere, measure the velocity of material erupting from its surface, and analyze the magnetic structure of a sunspot even before it rotates to face our planet. This 28th way space weather shapes our civilization is through the indispensable role of these space-based observatories. They provide the crucial data that feeds our supercomputer models, the raw intelligence that gives us a precious head start. When a billion-ton cloud of plasma, a coronal mass ejection, tears itself away from the Sun, these observatories see it happen in real time. They measure its speed and trajectory, allowing forecasters to calculate with remarkable accuracy whether it will deliver a glancing blow or a direct hit to Earth, and precisely when the shockwave will arrive. Without this continuous watch from the perfect vantage point of space, we would be utterly blind. The first sign of a Carrington-level event would not be a warning on a supercomputer screen, but the sudden, simultaneous failure of transformers across a continent and the eerie silence of dead satellites. Our entire strategy of preparedness, from safeguarding the power grid to protecting astronauts, hinges on the data streaming from these robotic guardians. They are the unblinking eyes that allow a technologically fragile civilization to live safely in the stormy neighborhood of an active star. That same interplanetary gulf we strive to cross is filled with a stormy sea of solar particles. Our robotic explorers on other worlds, like the Perseverance rover tirelessly working on Mars, are in a constant, delicate conversation with Earth. Their whispers of data and our shouted commands must travel millions of miles through the vacuum, a journey entirely governed by the solar wind. This 29th way space weather shapes our civilization is by controlling the very lifeline of deep space exploration. A sudden solar flare does not just create a beautiful aurora, it unleashes a torrent of radio noise that can completely drown out the faint signal from a distant spacecraft. Imagine trying to hear a friend whisper across a crowded, roaring stadium. That is the challenge our deep space network faces during a solar storm. Crucial data packets containing images of an ancient river delta or the results of a soil analysis can be lost to the static, creating gaps in our understanding of another world. The threat is so predictable that mission planners must work around a period called solar conjunction, the weeks when Mars or other outer planets move directly behind the Sun from our perspective. During this time, the Sun's scorching corona corrupts and blocks radio signals entirely, forcing a complete communications blackout. All rover operations are paused, and the vehicle is put into a safe, autonomous mode, waiting silently on the alien soil until the celestial alignment changes and the link to home is restored. This celestial schedule dictates the operational tempo of multi-billion-dollar missions, directly linking the Sun's moods to the pace of human discovery across the solar system. Every new image from another world is a victory not just of engineering, but of precise celestial timing, of successfully navigating the Sun's noisy domain. This profound communication challenge for our robotic avatars underscores an even greater imperative: the absolute necessity of protecting the human explorers who will one day follow them. These same cosmic forces that threaten our machines are an existential danger to the fragile human body in space. For an astronaut floating inside the International Space Station, or for a future crew on their way to Mars, a solar particle event is not an inconvenience, it is a medical emergency waiting to happen. The station orbits within the relative safety of Earth's protective magnetic field, but it is not entirely safe. During a severe radiation storm, the crew receives an urgent warning from mission control. Their response is immediate and practiced. They float quickly into a specific module, a designated storm shelter where the walls are lined with extra layers of shielding, often made from water stores or other dense materials that can block the incoming barrage of protons. This is the 30th extraordinary way space weather shapes our civilization by dictating the fundamental rules of human survival beyond our atmosphere. Every aspect of a long-duration mission is sculpted by this invisible threat. Spacewalks are meticulously scheduled during periods of predicted solar calm. A sudden flare can force a frantic scramble to bring astronauts back inside, cutting a precious scientific mission short. The entire architecture of a spacecraft destined for the Moon or Mars is not primarily about engines and life support, but about radiation protection. Engineers are pushed to the absolute limits of material science, developing new composites and perhaps even using the ship's own water and fuel as a liquid shield, creating a temporary fortress against the stellar onslaught. The dream of planting a flag on another world is at its core a race to outsmart the sun, to build a tiny, mobile pocket of Earth-like safety in the most hostile environment imaginable. This relentless focus on survival is forging a new generation of explorers who must live by a celestial forecast as intimately as a sailor reads the wind, a testament to our most profound vulnerability and our most determined resilience. The same invisible storm that threatens astronauts has become a powerful engine for invention. This relentless cosmic bombardment forces engineers to completely rethink the very substance of our spacecraft. They have moved beyond simple aluminum hulls, developing intricate composite materials that are both incredibly light and remarkably strong, woven with fibers that can absorb and disperse the energy of impacting particles. Specialized coatings are applied to the spacecraft's exterior, designed to bleed off the dangerous static electricity that builds up from constant particle strikes, preventing catastrophic discharges that could fry sensitive instruments. Inside, the electronic brains of these vessels are built with radiation-tolerant components, circuits designed to resist the bit-flipping chaos of a single event upset. The innovation does not stop there. Laboratories are experimenting with self-healing polymers, materials embedded with microscopic capsules that rupture when damaged, releasing a healing agent to seal cracks caused by radiation or micrometeoroid impact. Perhaps the most futuristic concept is the magnetic shield, a plan to create a miniature version of Earth's protective magnetosphere around a spacecraft or habitat, deflecting charged particles with an invisible field of force. This 31st extraordinary way space weather shapes our civilization is by acting as a relentless catalyst for advancements in material science. The technologies forged in this cosmic crucible do not stay in space. The same resilient composites developed for satellite housings are now used in the deepest trenches of the ocean, protecting submersibles from immense pressure. Radiation-hardened electronics find critical applications in medical imaging devices and the control systems of nuclear power plants, ensuring reliability in high radiation environments on Earth. The challenge of surviving our star's wrath consistently pushes human ingenuity to create stronger, smarter, and more adaptive materials, a cycle of cosmic pressure and human innovation that ultimately strengthens our entire technological species. Our ultimate vulnerability to the sun has forged a new kind of awareness, a cosmic perspective that reshapes our very identity. We are not merely inhabitants of a solitary planet, but citizens living within the sun's vast and dynamic atmosphere, our lives and machines subject to its invisible currents and storms. This is the 32nd extraordinary way space weather shapes our civilization by fundamentally altering our philosophical and existential view of the universe. The realization that a flare erupting 93 million miles away can darken our cities and silence our communication forces a profound humility. It shatters the illusion of our independence, revealing that our technological civilization is not a separate entity conquering nature, but a delicate layer of activity entirely dependent on a star we do not control. This understanding fosters a powerful sense of cosmic citizenship, a shared responsibility that transcends national borders. We are all equally passengers on a spaceship Earth, navigating the solar system's weather together. This expanded view is the essential guide for our future as a spacefaring species, a constant reminder that to survive and thrive among the stars, we must first learn to listen to the rhythms of our own. From the myths of ancient navigators to the vulnerabilities of our global power grid, we have journeyed through 40 extraordinary ways space weather silently sculpts human civilization. This exploration reveals a profound truth. Our destiny is inextricably linked to the dynamic behavior of our star. The challenges posed by solar storms and cosmic rays have spurred innovation in materials and medicine, fostered unprecedented global cooperation among nations, and even influenced our deepest art and psychology. As we continue to build a technologically advanced society, understanding and respecting the power of space weather is not just a scientific pursuit, it is a fundamental necessity for our survival and prosperity. Let this knowledge empower you. The next time you look up at the sky, you will see more than just the sun or the stars. You will see a dynamic force that has guided, threatened, and inspired us since the dawn of humanity. Share these insights, discuss them, and together we can build a future resilient to the wonders and warnings from our sun.